Hello everyone. Today we are going to be learning about nomenclature. So this is lesson 2.2. So our second unit, the chemical reactions, or the mole unit, and lesson 2. So nomenclature. So a pretty fancy word there. What does it mean? Hopefully you can maybe be looking at the prefix there, nom. You might have a little bit of a guess for this. Yeah, it is a fancy way of saying naming. So we're going to look at naming polyatomic ions today. So we did a review already on the binary compounds. That's compounds that just have two different types of elements. And now we're going to look at our polyatomic ones. So nomenclature. So basically, who gets to decide this stuff? So we have IUPAC here. So IUPAC stands for International Union of Pure and Applied Chemistry. So IUPAC sets the rules for naming. So why is this important, first of all? Here's a picture. So IUPAC was first established in 1919. So it was a group of chemists that got together, and most of their work is linked to standardizing naming. So why would you think this would be important? Why do we all need to have the same naming for different compounds? Yeah, so research is the answer. So scientists all over the world do research, and the underlying philosophy then of IUPAC is that, if we have this global scientific community and people need to be able to talk to each other and to understand everything that each other is saying. So I've just put a map here. These are all the major level 4 labs in operation worldwide. So there's not that many. So level 4 is like for biological safety stuff. So these are the major intense labs. And as you'll note, what's over here? That's Winnipeg there. We are on the map. We are one of the few places in the world that have a level 4 lab. And that's our virology lab, or our microbiology lab. And you'll see that on Arlington. So when you drive down Arlington, just over the Arlington Street Bridge, you will see this big giant building. So this is a world-renowned lab. So right now, for example, this will be timely for us this year, all the scientists who work in this lab have all been told to pull their own research and to focus on the coronavirus. So that's what's happening there. When we had the Ebola crisis a little couple of years ago, same deal. All the lab, this was one of the only labs that was able to legally work on the Ebola crisis. So of course the safety protocols are really intense, and I would encourage you, if you're interested in that, to do a little bit of research on that. And it's also really interesting when you sort of consider why Winnipeg. So think about that for a little bit, and maybe we'll talk about that in class sometime. Okay, so the main reason then, my whole point, getting off on that tangent, was to just talk about research. And so we have to remember that scientists are going to build off each other's research. So we need to have the same language. We need to have a common language there. And again, I like to talk about literacy and language in a science class. Really, really important, okay? So naming polyatomic compounds. So you have a list of polyatomic ions on the back of your periodic table, so I would invite you to get that out now so that you can follow along here. Those are the most common ones. There are others, but these are the most common ones, okay? So you always have that too with you in terms of assessment. So you never have to worry about sort of memorizing the real basic ones. Okay, so there's a naming pattern for radicals. So radicals is another way of saying the polyatomic ions. Okay, so just another word for that language-wise. Oh, sorry. Okay. All right, so the pattern. So first of all, you're gonna have the root. So this is the root of a word here, and then the ending, the suffix, is going to be ate. So of the polyatomic ions, so the one that's most common will have the root of the word and the ending ate. Now you'll notice when you look at all the polyatomic ions, a lot of them, the majority of them, have oxygen. So this naming pattern is linked to how many oxygens. there are, okay? And some of you actually would have taken this in your grade 10 course as well. Now, if we have one more oxygen than the most common one, you're going to use the prefix per, then have the root, and then the ending ate still. And then when we have one less oxygen than the most common, you're going to change the suffix or the ending to ite. So instead of ate, it goes to an ite. And then two less oxygen, it's going to be hypo as a prefix, the root, and then ite as your suffix there. So you can copy those down, and then we'll work through an example here. So ClO3 minus. So you look at that, and that one I think is on the back of your chart there, and so you will determine that this is the chlorate ion. Now, what happens if we add one oxygen? Oops. So if we add one oxygen, this is ClO4. Now, the ionic charge does not change, so sometimes people struggle with that. So the chlorate ion is always going to have a 1- charge, no matter what, no matter how many oxygens are there, okay? So this is ClO4-, so one more oxygen. I'm going to look here. I'm going to use the prefix per, keep the suffix as ate. So this will be perchlorate. Now, one less oxygen is going to be ClO2-, and if we look back at the rules, you're going to change the ending to ite. So this one is going to be chlorite. And then two less oxygens, and I'm just going to write ClO-. This one is going to be hypochlorite. Good. Now, let's go through the SO4 2- one. SO4 2-, if you look it up, is going to be the sulfate ion. I spell my sulfate with PH, but you can use an F. Either way is correct. Now, if we have one more oxygen, that's going to be SO5 2-, one less oxygen, SO3 2-, and two less oxygen is going to be SO2 2-. So what are the names going to be? This one, persulfate. For the one less oxygen, we're going to change the ending ate to ite. So this is going to be sulfite. And then two less oxygen from the most common. So remember, the most common, that's sort of like where you start, right? And this one is going to be hyposulfite. Okay, good. Now, we're going to put it together. Now, all the other naming rules are going to apply. So the ones we talked about with binary compounds still apply, which means the first element, so in an ionic compound, the first element that's named is going to be, you're going to say it fully. So the first metal, you say it fully. And then the second part here, you would apply the other rules. We also want to use the stock method, right? So any of the transition metals, we want to use the stock method. So that's our Roman numerals, right, in brackets. So we're going to go through and just do these here, but I would like you to pause the video here and try it on your own, okay? So going through, this is going to be magnesium sulfate. Now the next one, this is magnesium again. PO4, so if we look on the back of our periodic table, PO4 is going to be phosphate, the phosphate ion. So this would be magnesium phosphate. Now the next one, we've got calcium and we've got PO3. So now instead of phosphate, you're going to say the metal as usual, so calcium, and then this is going to be phosphite. Okay, so you're changing that ate to an ite. Next, calcium again, and then ClO2. So ClO2, so chlorate would be ClO3, so this is going to be chlorite. Next one, sodium, and then we have hydroxide. Okay, our next one now, tin. Tin is a transition metal, so you're going to have to use a Roman numeral to indicate the charge. Now, ClO4, if you look at ClO4 minus, you know that it's got a 1 minus charge, okay? So if it's got a 1 minus charge and there are 3 of them, the overall charge coming from the hypochlorite here, the perchlorate, is going to be 3 minus, which means this tin has to be 3. Oh, no, wait, hold on. I think I have a mistake here. Oh, I did, sorry. I changed this to a 2. That's not supposed to be a 3. I was wondering about that. Okay, so sorry about that. So if we change that to a 2, 2 minus then is coming from the hypochlorate, the perchlorate, which means this has to be 2 positive. So this is going to be tin 2 perchlorate. Okay, now you have to be able to go the opposite way, right? So you have to be able to look at the name of something and figure out what the bonding ratio is. So looking at this, lithium I know is 1 positive. Now hypochlorite is going to, if I look at chlorate, is ClO3 minus. Now I need 2 less oxygens there. So this is going to be ClO minus. Now, because I have 1 positive from the lithium, 1 minus, from the hypochlorite, this molecule then is going to be LiClO, and that's it. Okay, so that is lithium hypochlorite. Next one, potassium sulfite. So again, potassium is this. Sulfate would be SO4 2 minus, but because it's sulfite, it's going to be SO3 2 minus. Now I'm going to need 2 potassiums to balance off that SO3, so K2SO3. Next, we've got iron 2 perbromate. So when we have the prefix per and the ending ate, that's going to have 1 more oxygen. So bromate should be BrO3. So I'm going to have 1 more of that. So the iron is 2 positive, and I've got BrO4. And that's, 1 minus here. So now, looking at how these are bonded, I'm going to need 2 of the perbromates to balance off that iron. So when you write them this way, you're going to go Fe, and then in brackets for the whole thing, 2. So it's important to note that. So you take this, and the whole thing has to be in brackets then, and then you're going to use your subscript to balance that. Okay, we will go through more of these in class, and we'll do some practice because for some people it takes a while to get the hang of them. But exercise 3 is assigned to you, so you can give that a try, and I'll try to post the answer key for you for that too. Okay, thanks everyone.